So yesterday we learned about solving systems of equations by graphing, and today we're going to find that there's another algebraic method that can be used to solve systems, and that is by substitution. So our three are to be able to set up a systems of 2 or 3 equations and use substitution to solve them, recognize properties of systems of equations, and then use systems of 2 or 3 linear equations to solve real-world problems. So the counter here that we've not seen before. You're going to be asked on occasion to identify if a system is a consistent or an inconsistent system. A consistent system is one where there's one or maybe more than one solution. An inconsistent system is when there are no solutions. In other words, if we graphed those equations, they would never come in contact with one another. So we'll want to be able to identify whether a system is consistent. So we're going to start with this example where we are given a system of equations. Now the formatting didn't come out real great here. So this is really supposed to be x plus y equals 6 and y equals x plus 2. In fact, I think I'll write it a little bit bigger down here. Y equals x plus 2 and x plus y equals 6. Yesterday we mentioned that when you see this bracket, that basically implies the word and. So we're finding values of x and y that satisfy both of those equations. Well, you'll notice in this equation we're told that y equals x plus 2. So that means that in the other equation, wherever we see a y, it can be replaced with that quantity. So I'm going to take this second equation and I'm going to rewrite it, and instead of saying x plus y, I'm going to replace y with what I'm told it equals, which is x plus 2. And what you'll now notice is that you have a single equation with one variable, and we can find that one variable. And once we find it, we can substitute it in to find the other. So we'll combine our like terms. X plus x is 2x. So we'll get 2x plus 2 equals 6. We know to undo the addition next, so we'll subtract 2 from both sides. And we'll end up with 2x equals 4. And finally, we need to undo this multiplication with division, and we end up with x equal to 2. So the x-coordinate of the point of intersection for these two linear equations is 2. Now to find the y-coordinate, it's very simple if we just choose to use this equation right here. If I use that equation right there, I'm just going to rewrite it, y equals x plus 2, but I'm going to replace x with what I now know it is, which is what I just found to be 2. So I get y is equal to 4. So these equations will intersect one another on the coordinate plane if we graphed them at the point 2, 4. Now we can verify that this works. We can go back to each equation and we can substitute 2 and 4 in and make sure they work. So in equation 1, 2 plus 4 does equal 6, and in equation 2, 4 does equal 2 plus 2. So our solution is correct. 2, 4 is its point of intersection. Let's try another. Here I have a system of 2 equations, and these are going to be a little different in that they are not linear equations. Do note though, well, they're not both linear equations, I should say. I'm told that y equals 4x in this first equation. So that means wherever I see a y in the second equation, I can substitute in a 4x because they have the same value. So I'm going to do that. I'm going to rewrite the second equation. xy, but instead of y, I'm going to rewrite y or replace y with what I know y equals, which is 4x. And again, what you notice is I have one equation with one unknown. So I'm going to go ahead and multiply x to the first by 4x to the first, and I get 4x squared. Then I know to undo the multiplication next by dividing. And now I have x squared is equal to 9. So to get rid of squaring, I have to square root. But we've got to remember there are two square roots of 9. There's positive 3 and there's negative 3. So I'm going to have 2 points of intersection if I were to graph these. One that has an x-coordinate of positive 3 and one that has an x-coordinate of negative 3. I'm going to find each of their corresponding y-coordinates. So I'm going to substitute 3 in for x. If I substitute 3 in, y is equal to 4 times 3 or 12. I'm going to substitute negative 3 in for x. If I substitute negative 3 in, y is equal to 4 times negative 3, which is negative 12. This is a consistent system of equations because it has at least one point of intersection. In fact, this one has 2. And once again, I can check to make sure they both work by substituting them into both equations. I already know they work in the first equation. If I try the second, 3 times 12 is 36. And if I try the other solution, negative 3 times negative 12 is also 36. So my consistent system of equations in example 2 has 2 solutions. Now in example 4, I skipped my originally planned example 3. The directions are a little different. It says describe the graph and the solution. So you're given this equation, y equals 2x squared. We know that that's a parabola when graphed. But you're also given this equation, 3y equals 6x squared. And I don't want to have to graph this equation to be able to describe it. I should recognize that it's to the second degree, or second power, so it's a parabola. And I can just solve the second equation for y by dividing both sides by 3. And I'll have y is equal to 2x squared. Well, compare. The first equation is exactly the same as the second equation when I simplified the second equation. So they're really the very same parabola. They sit right on top of one another. And what that means is they represent a consistent system of equations because of the fact that they have at least one point in common. In fact, all of their points they have in common. So again, if there's at least one point in common between the two equations, then you have what's called a consistent system of equations. Okay, finally. So let's look at this last example. The drama club printed 1,750 tickets for their spring play. They printed twice as many student tickets as adult tickets, and they printed half as many children's tickets as adult tickets. Write a system of 3 equations and solve that system to find how many tickets of each type were printed. Well, what I know is that I have adult tickets, and I also know that I have children's tickets, or student tickets and children's tickets. So I'm going to use A for the number of adult tickets, C for the number of children's tickets, and S for the number of student tickets. Well, from this fact here, I know that their total is 1,750. That means when I add the number of each of those tickets sold, they should add up to 1,750. Then I also know that their are twice as many student tickets as adult tickets. So in other words, if I wanted to set the student tickets equal to the adult tickets, since there are twice as many student tickets, what I have to actually do is to double the adult tickets to make them the same. Or I could have cut the student tickets in half to make them the same. But I find working with a number 2 is easier than working with a number 1/2. The last fact given to me is that half as many children's tickets are sold as adults. So again, if I want to make the children's tickets equal to the adult tickets, and there are half as many children, then I have to double the number of children to make them equal to the number of adults. A little bit tricky there, eh? So here's my system of equations, and there are 3 of them. I want to solve. So what I know is that S is equal to 2A. So wherever I see an S, I can replace it with 2A. I'm going to do that right away here. So when I take, excuse me, I lost my pen here. So when I take this equation here and I replace the S with 2A, I'll have A plus C plus 2A is equal to 1,750. Now my problem is I still have 2 variables in that one equation, and to be able to solve I need to have just one variable in that one equation. So I need to determine the value of C in terms of A. Well, I can do that using this equation. I want to solve this equation for C. I've got 2C is equal to A. To get C alone, I'll have to divide by 2. And so I get C is equal to A over 2. So I'm going to replace it with A over 2. All right, so that's like a half A. So what I basically have here is I have 1A plus 1/2 A plus 2A. And those clearly add up to 3.5 A. So I have 3.5 A is equal to 1,750. To get A alone, of course, I'm going to need to divide by 3.5 on both sides. So I'll find that the number of adult tickets is 1,750 divided by 3.5, which is 500. That's the hard part. Now the easy part now is to figure out how many student tickets and how many children's tickets. And I can find that out easily using these 2 equations. Student tickets is equal to 2 times A, which would be 2 times 500. So the number of student tickets, sorry I'm running out of room, would be 1,000. And I already figured out the number of adult tickets is 500. Now I need children's tickets. Well, I can use this equation. I know the number of adult tickets is equal to 2 times the number of children's tickets. So 2 times the number of children's tickets is equal to the number of adult tickets, which is 500. And to get the number of children's tickets alone, I'll have to divide by 2, and I get the number of children's tickets equal to 250. You'll notice that those all add up to 1,750 as they were supposed to. You'll also notice that the number of adult tickets is twice as many as the number of children's tickets, and that the number of adult tickets or number of children's tickets is half as many as the number of, hang on, I'm saying this wrong. I have twice as many student tickets as adult tickets, and the blue underlined, I have half as many children's tickets as adult tickets. So I know those work in all 3 equations in my system. So that applies solving systems using substitution to a real-world situation. Best of skill to you as you practice applying some of these in your homework here in Lesson 3. We're doing numbers 1 to 15 today.